Today we're going to be talking about open theoretical questions, which Vivian has offered to kind of go through an overview she had put together, and then just kind of, yeah, hopefully have some interesting discussions around those. Over to you, Vivian.
All right. Okay, so I think you've all seen a bit of a teaser on this, but thought it might be worth to dive a bit deeper and go into each of the open questions in a bit more depth, just so they're more concrete and on top of everyone's mind. And if you're ever taking a walk and looking for something to think about, uh, you can come back to those. It probably won't take that long to go through these, unless we have lots of discussion on them. But let's see. So yeah, there's this Excalidraw board with various topics of open questions. I try to kind of group them by overarching topics, but basically where these red boxes come from is from this Monty capabilities roadmap, with all the capabilities we want Monty to have eventually, and kind of prerequisite capabilities for those. And the ones that are marked in red are the ones where we currently don't have an idea of how we would implement those, or are uncertain about the ideas that we have. And so this is by no means a comprehensive list of all the open questions we have. It doesn't really include open questions around like the biology of things, for example, like which layer, what connectivity would support this. This is really more about the conceptual open questions on like what conceptual problems would we need to solve for Monty to have the capabilities of the neocortex. And even in that scope, I might have missed things. So if you think of things that are not here, we can add to that as well. Um, does that make sense so far? Should I just dive in?
Mhm.
Okay, so I looked at this earlier this morning and I noticed it's already getting outdated. I think I wrote it in May, so now it's 1st of July. Uh, but anyways, you can already see on the first box, attention, segmentation, and input sharing. This is the box that Scott and Niels are starting to work on right now on the research side and prototyping some of the ideas we had, and we talked about those at past research meetings as well. But basically, one of the larger open conceptual questions is how do we implement attention? What even defines attention? Is it like a region in space? How is that region defined? What signals can change that region? Like we talked about model-free signals and model-based signals. What does this region do? Like we talked about it constraining where you move, constraining where you get input from, constraining which columns vote with each other. Are there any other roles it would play? How would it work in conceptual space, like non-physical space, if you're just mentally imagining things and moving your attention around there? Like if you imagine your living room right now and walking through that. Um, and so yeah, we're kind of getting started on that, thinking about um, defining model-free attention using object segmentation and kind of defining regions there. And I think that project that Scott is working on now will give us a lot of answers to that. And then Niels, you're also thinking about the model-based part of it. And so hopefully that's one we'll talk a lot more about in the next weeks and months. Um, And then related to this one, we have segmenting objects based on model-free and model-based information and based on moving parts of objects. And so, yeah, seems necessary that we have the ability to segment objects. Um, like we can't always assume that we learn models in the void, and we need to stay on objects to recognize them. And yeah, there are many principles we might use for segmenting objects, like Gestalt principles like proximity, continuity, similarity, figure of ground, common fate. I think I showed a figure of that last week, like all the different principles that are out there in psychology that people use to group things or segment things. And so I think, at least on the model-free side, we'll also get some answers there from Scott, hopefully in the next weeks on what actually works, at least for our purposes right now, but then probably need to add more complexity in the long run. And then again, related to Scott's project right now, leveraging a policy to stay on an object, which combines model-free segmentation and using that to define an attentional region, and then using that to stay in that region. Um, does that any thoughts, comments, questions on these? Um, and then yeah, this one is slightly like this one is not one we currently work on, and not related to those previous topics, which is sharing input with many learning modules. So that's kind of the shared learning problem. I mean, it might be related to attention, but basically the fact that only a small portion of our columns or learning modules will actually be on the object that we're trying to learn about, and a lot of them won't be on it. But so what are they learning? How are they learning about the object? How can you learn about an object with moving your finger over it and then recognize it with your other finger or with your eyes? And in the past, we talked about some ideas around that, like columns outside the attended area could receive input from the attended location. Um, Still unclear on like whether they could receive features or only locations. If they would receive features, what kind of features would that be? Would it only work with object ID features, or could it also work with like raw, like sensory, like at the lowest level of the hierarchy, the sensory features? Um, those are, yeah, the kind of open questions around that. Another idea we talked about in London and afterwards was that the input from sensors could be rapidly replayed and broadcast to many columns between sensations. That was more about sharing input during the inference phase instead of the learning phase. So that was kind of an idea as an alternative to voting, where instead of voting on locations laterally, uh, if I if I grab a cup with 5 fingers, my index finger, after it actually gets its own sensation, gets a replay of the sensations of the other 5 or other 4 fingers. I don't have 6 fingers. Um, and that could, yeah, solve some of the problems we currently have with the voting on location algorithm. But then again, that's limited to replaying a few locations. You couldn't do it with thousands of them, like all the patches on your retina. You probably wouldn't do like a raster replay of everything on your retina to every other column in V1. Um,
It's just kind of occurring to me, I guess, that a lot of attention and model free stuff, it just feels egocentric. Like that's kind of a defining characteristic, at least in terms of the way I'm thinking about it. Whereas model based stuff feels more, like the object is in its own reference frame. I don't know if that seems right to you guys, but
yeah, definitely the first part that it feels like attention seems like an egocentric concept, like attending to an area in space
mhm.
relative to your body. So when you say the model-based part feels more object-centric, um, do you mean how it's derived and then it would still be translated, or you mean like all the
I
way?
mean, like the learning module is operating in the object's reference frame. Um,
Yeah,
I mean, there's no reason the learning module can't be turned on the person and also operate on a person's reference frame, but I just mean in terms of this sort of object world that we're in most of the time. The learning module is operating primarily in the object's reference frame. It's, you know, whereas everything, so I guguess that's why I said
Yeah,
model
okay, yeah.
based, but
Yeah, as in to kind of contrast it.
yeah.
Yeah, I think I also agree with that, and but I guess just with the egocentric for attention, like it can it still feels like it needs to update in order to kind of be stable or relevant. As in what I mean is like if you're walking around a room, technically in egocentric coordinates, the like if you're let's say I'm focused on a chair and I'm walking towards it, technically in like all egocentric coordinate spaces, that object is constantly moving. Um,
Right.
but I don't think that's to say it's not in an egocentric space, but it's more just that the attended location is updated so that it maintains stability, or kind of relevance as you
Mm.
move. Um, but like
Yeah,
an alternative would be if we were attending in a room space, then that would be fixed as you walked around the room. But I'm not saying we do that, but yeah, it's just one thing to kind of think about when we talk about like egocentric in the extreme, the limitation of that is that as you move, representations become outdated. Um,
Mm.
yeah. I guess,
and
yeah.
that's especially the parent, like if
Right.
you are, it's like more sensor centric or like, I don't know, head centric, like you turn towards a sound, it's like, well, you didn't lose track of where you were attending to. Um,
Fair
Yeah,
point. Yeah.
in my mind, it feels like there's this kind of common space, whether it's egocentric or anchored to your environment, the room or something. Not sure, but a common space. And in that space, you're attending to a location, and learning modules, if they want to change the attentional window, they'll use their model. So they originally derive it in a model, the model's reference frame, object-centric reference frame, but then it has to be converted into this common space. But also
Mhm.
with sensor modules, I'd say there needs to be a conversion from the sensor's reference frame, like retinal space or something, into body-centric reference frame. And with some sensors, it's really straightforward, like your finger is like probably already tracking its location relative to the body, but with others, um, like retina, it might be a bit more involved.
Okay.
And yeah, please come, like jump in and bring up thoughts and ideas. Like it's not supposed to be just a presentation to listen in.
do we have something here? I mean, maybe it's not so much an open question, but on kind of how attention constrains sensory inputs and like implications for voting, I guess. Um,
Um,
yeah, attention area can be used to gate which columns are receiving. Um,
yeah,
yeah, okay. I guess that's um,
yeah, I could add and which comes what with each other. Don't think I
yeah,
listed that yet.
But I have a
right.
question that I think it was kind of implicitly kind of, or I don't know if this is decided, but do we think that the attentional area slash region slash volume is like this like spherical blob of space, or like that attentional region is like locked into the shape of the object? Like if I'm focusing on mug, then it's the attentional area, the exact morphology of the mug, or is it just kind of this, sphere blob like around the mug, like a heat map? Kind of like, okay, like I
Yeah,
have,
I'd say it's an open question.
okay,
Um, I think, yeah, I think we talked about several, like all these options you just named before, but I don't feel like there was a strong consensus for one of
yeah,
them.
Right. But yeah, it feels like we're at least trying maybe the more flexible one to begin with, which is kind of like a amorphous cloud, which
yeah,
might, if you're kind of lucky, or if, that might kind of conform exactly to like the shape of a particular object, but in general, it probably wouldn't. And
Yeah. I just had a
yeah.
thought, but maybe when it's model free, it's like an amorphous blob. Like if I'm hearing a sound like loud boom somewhere, it's like, okay, in my egocentric space, like there's some region where there was like a loud sound. But then when it kind of combines with model-based attention, that's when it can kind of sharpen to like a that object. Because I'm thinking about, like the basketball throwing with the gorilla passing by. Like we're really focused on like the ball itself that we like miss, even though the gorilla is like passing by behind it. So if it's just amorphous blob, then we would have noticed the gorilla because that's part of the intentional area. But if it's like locked into that ball somehow, then yeah, like a lot of people the first time they miss it. So
Yeah,
I
I
don't know.
think
I
that
mean, just
no,
an
I
idea,
mean I
right?
think that fits with yeah, I think what we've been kind of thinking, and I think one of the open questions related to that is, yeah, assuming model based is a bit more, as you say, kind of sharp, and presumably model informed. The question is kind of how is that defined in the attention space? So that's where I think last time we talked about like maybe there's some way the learning modules can almost kind of communicate sort of the shape of an attention area. Like a single learning module could kind of say like this is the boundaries of where you should attend to, or maybe because we have hundreds and thousands of columns all talking about an object, by each contributing a point, that might sort of implicitly define like a shape of an object. I think those are kind of the two main possibilities we've discussed, but it haven't kind of agreed which of those make most sense.
Yeah.
And it may be one of those cases where Monty doesn't have to do what biology does, but
Kind of does make me think of, um, well, I do think about like polar coordinates and that kind of thing in terms of egocentric, but that also makes me think about the an open question about 2D to 3D, like, looking at an image of a cup. I can still recognize a cup even though I don't have the full 3D um, sensors, right? Whatever that projective geometry is, however that happens in the brain, I guess is something I've never really worked out myself. I don't know if that's
yeah, actually, is that
on
on
open
here? We
question.
definitely, it's been an open
Yeah,
problem at some point.
yeah, I was just gonna say I think we should add that. Probably add it to scale and deformations topic
Yeah.
overall. Um, Maybe we call it estimating depth from 2D images. Would that capture it? Like you get, oh, I think you
Yeah,
mute me.
maybe. Although, yeah, I don't know if that presupposes the solution, because I guess that's one possibility.
Right.
I think at one point we called it recognize objects in 2D that have only been seen in 3D. Because I'm not saying this is the case, but maybe there's, I don't know, maybe at the same time as we're learning a 3D model, we're learning some like implicit viewpoint type model or something, and that's what we're recognizing with.
Yeah,
But yeah, but
yeah,
I
I think
think like you say, kind of estimating 3D from sort of monocular cues is one thing that could help with that.
yeah, and I think it's actually uh, been one of the capabilities we listed on the
Yeah, for a long
original
time, I
overview.
feel like going
Yeah,
back to the like origin of Monty.
yeah, like this very first spreadsheet we have. What's, yeah, recognize object learned in 3D and 2D. Um, so yeah, I'll see what adding this in here somewhere. I guess it will be under recognize objects and they pull this under all conditions.
Hmm.
So I'll just yeah, take this one. Try to fit it in here. Yeah, because I
Yeah.
don't think it's covered here yet. You could look at it as some type of deformation, but it's a very specific type.
Yeah.
Yeah, okay, that's a good one, Scott. Any other thoughts we should list down here on solutions? Or
I guess just yeah, like uh sort of native 2D models maybe would be one way of describing it. Um so as in like I
like
guess if we
models learned with the 2DSM
like
for the
yeah, as in
object.
like when we're looking at the 3D world, maybe we're also learning 2D models that that would kind of naturally generalize or like match. Um which is almost like yeah, like most computer vision and deep learning doesn't even deal with depth at all. Um and binocular inputs and kind of
Yeah,
just assumes everything's 2D and that can work reasonably well.
right. Um,
And yeah, just the last thing on that, there is some evidence for this like concept of like a canonical view of objects and that people recognize certain objects quicker from certain viewpoints and have a tendency to what you call it? Yeah. Uh, like imagine those objects from those viewpoints and stuff like that.
yeah, yeah, that canonical way of drawing a house or a
Right,
t-shirt
exactly.
or a tree. It's like
Exactly.
you almost never see a house like that, but
Right. Yeah, like you I think it's pretty much impossible to see a house without some sort of like volumetric perspective um, on like yeah, um, and yeah, and you can imagine maybe it's a mixture of these where like if something's present in this like close to this canonical view or like close enough of a match, then we can use that. If it's like really far from that, then we need to kind of again a bit like scale invariance. We sort of need to trigger like a slower like okay based on what I think the depth is, how would this match with um, like my 3D models and stuff like that?
yeah,
I don't know if it's worth having something here as well on like the related problem feels like things like the Necker cube. That's kind of like how do we infer 3D? Because there's like recognition, but I don't know, maybe it's the same thing, but that's kind of like inferring 3D shape from 2D images. I don't know if it's the exact same.
yeah. I feel like it's the first part, like estimating depth based on monocular cues, maybe.
Yeah. But what's weird is
It just
like with the
fails in
Necker
that
cube,
case.
it's kind of model based. It's like I don't know if there are model free signals um,
Yeah.
that we can use. It's almost more like I don't know.
Is that how you spell the Necker cube?
Yes, yeah.
It's published as a rhomboid in 1832 by a Swiss crystallographer. Interesting.
The Necker cube?
Yep. Named
That's interesting. Wait, so when you say crystallographer, as in like someone who studies crystal objects?
I'm assuming crystals and crystalline structures,
Yeah,
but
and then
yeah.
and so like that person wasn't necessarily interested in like the psychological element, and then someone noticed it was ambiguous or like bistable?
That's a good question.
That'd be interesting if it was, yeah, like
Yeah.
Okay, should we go to the next topics? Or are you finding
yeah, no,
something?
sounds good.
Yeah. I can read about Necker later.
Yeah, that's not defensive. Yeah, while we're here on scale and deformations, because I think we got everything on the attention and input sharing. There's also still that good old problem of scale, which we talked about since the beginning of Monty, and always kind of said, well, yeah, it shouldn't be too hard, but wasn't ever really a priority. But we don't really know uh, whether what we're thinking will work out or whether there's a more elegant solution. So the kind of one idea is that we could deal with scale the same way as with orientation. So it's just another variable that's inferred by the learning module and applied to the incoming movement vector. So we're inferring, like the same way as we're inferring rotation and rotating the movement vector, we would also have hypotheses about scale, and those would scale the movement vector. And of course, that adds kind of another combinatorial dimension to our hypothesis space. So we would need some additional ways to make it more efficient, like how do we not test all the possible scales? I think, like, for example, the worst sampling work from Rami makes it a bit easier now to add new hypotheses. There might be other things like the displacement LM could be used to very quickly estimate scale. I don't know how familiar people are with displacement LM, but it was basically the very first learning module in Monty. And instead of using nodes, so features at locations for the matching, it would use the edges in the graph to recognize objects. And when you use the edges, you can match those in a rotation and scale invariant way, rotation, translation, and scale invariant way. And so it was a very efficient and well-working method to recognize objects in any rotation, location, and scale. But the big issue why we didn't continue with that approach was that you had to traverse the same edges, so take the same movements as you did during learning. You could take those movements in a different order, but if an edge wasn't stored in the graph and you took that movement, you wouldn't be able to recognize the object anymore. And that's like a pretty unrealistic assumption to say that like only paths that you've taken before can be used to recognize an object. And so that's why we kind of moved on to using feature set locations. But it still had this advantage of being able to recognize scale very quickly. I actually added an item on our future work pages last week. Um, uh, so yeah, it was scale invariant, which our current learning module is not. And so one idea is to actually have a hybrid learning module that is evidence-based, but it also stores some edges, so the most commonly traversed paths on an object, like moving between the eyes and the nose and the mouth of a face. And you can use those to very quickly narrow down the rotation and scale of an object if you see them, but if you don't take these paths, you still have the evidence-based, location-based approach to recognize the object with a completely novel path.
I guess one thing I would maybe add or consider adding is model-free like model-free information to get initial scale hypotheses, something along those lines.
Right.
Um,
Yeah, I think Yeah, exactly. Yeah, model free and also kind of a bias uh, for certain.
Yeah.
Like I'm probably not going to initialize my elephant hypotheses when I'm looking at something the size of a mug. Ah, but
Right.
yeah, we'll
When
see.
we say
In Rome, or if anybody brings an elephant mug.
Yeah. Um,
yeah, when we say scale, um, in people's mind, is this the same as inferring the size of the object, or is this a separate issue?
Yeah, it's the size.
Okay. Um, I mean, so there's one way that we could kind of yeah, I mean, one way that we could infer size is if we know the depth of it, then well, let's see. Um, yeah, if we have two eyes and we know that the object is, like occupying about like 2 degrees in our retinal input at a certain distance, then that information, like by drawing like a triangle, we can actually figure out like, okay, this is about like 30 centimeters, like, or whatever, using depth information. Like, uh, there's a way to, I guess, calculate it if we're seeing this like
yeah.
in like if we're seeing like a mug in a void, the depth and how much of that object covers your field of view can tell us like approximately like this is about in this, like tens or meters or whatever. But
Yeah,
also
which I think is an
scale,
example of kind of a model free. Yeah.
Yeah.
yeah. Um, but I mean, this is a different story when we're looking at like a picture. I think somebody shared like a huge like chair in like the middle of the city, and that's like
Yeah.
yeah. I
It's a
mean,
German furniture brand.
I see. Yeah, it was very like memorable. So obviously, like like for that one, I mean, but in this case, like we are not looking at 3D, we're looking at a 2D picture. And in this case, the scale here is more like relative to kind of everything else around it. I guess it's less relevant to us right now because everything is in void. Like we don't deal with scenes at the moment. Um,
Yeah,
anyways,
but
but yeah, but if we're thinking about just like 3D void and whatever, like we can use depth information and how much we see in our camera to infer the size.
yeah, but that's a good other note that scale is often kind of defined by the relative size to other objects next to it, at least
Right.
in images.
Yeah.
In one of those pictures, when it was kind of an aerial view, it almost made it look like a tiny town. But when you see it, the chair from the bottom, then it's like, okay, that's a huge chair. It's just kind of
Yeah.
funny, like because you're not used to seeing chairs from below.
Mm.
I'm not.
Yeah, like I don't know, when you're in a plane and you look down at the cars kind of driving, they tend to just look like kind of like toy cars, um, rather than
Right?
normal cars that are really, really far away.
Yeah, I don't know what to do with that observation, but um, kind of funny.
Yeah, the one in about relative size, it seems like that's the kind of model-based priors. Like if you're looking at an image and you see certain objects, you recognize them, and then that gives you a prior of what the scale of the other objects will be in the image.
Right.
Yeah.
Um, but then, yeah, there's also this effect of like if you blur the edges of an image, it looks like a miniature. Uh, like if you have a photograph and you blur the edge, it looks like you took a picture of a miniature reconstruction of it. I
Uh,
don't know. Are you familiar with
Yeah, you
that?
mean
I
the
don't know
blurring
what.
the foreground and the background. What's it called? Tilt blur or something like that?
Yeah, like this thing
Oh,
where
shift, something like that.
um,
Interesting.
again, I guess this is all about depth cues because they're the depth. Like if this was a real scene, you would get like very different. If those things would be at very different depths, but in a miniature
Oh, I
scene,
see. I see.
they're
I see. I
almost
see.
the same. Like if your eye adjusts its
Oh,
focus.
yeah, yeah, yeah. Okay, okay, okay. Yeah.
Yeah, like
Um,
basically, I think we're basically used to when you focus in the distance, things in the foreground and background of that distant point are all in focus. Whereas if you focus
Yeah,
on like your finger, then even like a finger just in front of that finger or behind is out of focus. And yeah, so like you say, it's kind of like a model-free cue um, for the sort of absolute depth.
yeah. But yeah, I think all those are about just depth cues, which aren't necessarily about scale itself. It's more about like what movement information are you getting as input, and then that determines what scale is recognized.
And is it worth maybe just talking through an example with the displacement one? So yeah, let's say we just store displacements for like a handful of things. So let's say when we recognize faces, we have like the displacement between the eyes and the mouth.
Yeah,
And in our model, we were learning that at a particular distance, but I guess we were kind of tracking the actual displacement. So um, kind of let's say 3 centimeters, 5 centimeters. Um, Now we see like a miniature on a table with a head, but it's like now it's like 2 millimeters and 5 millimeters or whatever between them. Um, yeah, in terms of like how it matches on. Um,
um, yeah. So basically, you'd be getting feature input, which could be like object ID of the eye, nose, mouth, or the raw features from the sensor, and the displacement element. If you see one eye and then you take that displacement and then you see another eye, um, it stored exactly that displacement between the two. It could immediately match them even if the distance between the two is different or the orientation between the two is different.
yeah, so like
Um,
the match does not rely at all on the actual distance that was used train learning. It basically it relies just on there being kind of like an edge between those features.
right, and then the
But
relative
then you'd
distances
scale.
between consecutive movements.
Right. Yes, right.
So
Because I think that's a
in the
detail
next
worth
one,
describing that. Yeah, then so for the first match, you don't care about that displacement
yeah,
size. But
basically
once
for
you've
the first
matched
match,
it, yeah.
for,
Uh,
for the first match, all of the edges are possible, like no
yeah.
matter whether they're short or long. And
Yeah.
then that determines the scaling factor for the consecutive movements, and then you see if they're consistent.
Yeah, which I'd almost, well, I guess, yeah, I guess it's because the later steps is why it's called the displacement LM. But to me, like, that's almost like an edge LM or something like that, or like graph LM. Because like a displacement in some contexts at least implies like a, like a length. Whereas at least for that first match, it's like an edge match, or like a link. Um,
Yeah,
Anyways, I just think that's important to highlight conceptually because I think when I first came across the displacement LM, I assumed even that first match was still caring about that distance, which is why I was like, well, how is that actually scale invariant? Like you'd still need to try multiple scales.
yeah,
And
yeah, right.
and
It's
which is
an
another reason
edge
why
mapping.
like it would be good as a hybrid method where like we just store these for like a few really key edges and not for everything because otherwise that space explodes.
Yeah, yeah. That was the main issue that like there's just a combinatorial explosion if you want to have enough generalization. You have to store tons of edges and then you have tons of hypotheses. Um, but yeah, I think especially now with the salient CSM and being able to move to those salient regions quickly and between them quickly, I think it's more realistic that a hybrid approach could work.
Yeah, and compositionality, because like you say with the object IDs, like if we're seeing surface normal, that doesn't really constrain the
Yeah,
space much. But if we see logo handle, it's like, oh, okay, I might be looking at a mug, whether that mug's the size of a house or the size of, yeah,
yeah. Yeah, and even without the saliency policy, you could have a very simple heuristic of looking at the edges of or outlines of an object first, and that could very quickly define the size of it. And then you can move within that and use the normal evidence matching.
yeah,
Okay, so that's the stuff on scale. I guess one, like, it's also not like this doesn't necessarily need to be the solution in the end. I think something we explored every once in a while is that columns at different regions in the hierarchy are specialized for different scales. And so basically just depending on where you're in the hierarchy, you have priors on which scale you expect the object to be. But that also leaves some questions open, like with that chair, like if you've never seen a chair that large, how do you then suddenly recognize it? Um,
yeah. I remember someone, on Discourse once asking about like if you're an astronaut you're looking at Earth. Like, what is the scale of the learning module that is learning that? Like, is it astronomical? Like, which is a fair question. But yeah,
um, okay, then very different topic. I just put it into the scale and deformations box is deformations. And specifically like volumetric deformations. So like the balloon inflating, um, like something where it's not just something rotating relative to something else, but it's actually like all the different parts of an object are moving in different directions. Um, and so we talked about that various times before in the context of object behaviors. And I guess some solutions are, we could use scale as part of the solution, like an inflating balloon is a bit like scaling up a balloon. It's not exactly just scaling up, it's still deforming. But you could assign kind of scale on a more location by location basis, potentially. Um, Another alternative was to learn morphology keyframes and then interpolate between them, or like applying behavior model to morphology, but we didn't really find a great answer there on how to do that. So yeah, I think yeah, we had various ideas on this problem, but then uh, to me it's still not resolved how we eventually want to do that.
yeah, and I feel like with this one lingering thing is always like, to what degree do we expect the brain and therefore Monty to solve this? Like, for example, these solutions, one or a combination of them might not be perfect, but they may be good enough. Like um, in the same way that like you know generative AI can create photorealistic images of various things. That's not something like brains are just like constantly doing is creating generating in a photorealistic or like if we're drawing or whatever. Like there's things basically where we are inherently limited in our ability to do stuff. So yeah.
Yeah. Yeah, but it still seems like we're able to do it to some degree. Like
To
you
some
can
degree, right?
imagine a balloon inflating, you can imagine pushing on clay or Play-Doh and you know
Right.
how to deform.
And
And
you'd be
so,
surprised if it, yeah, did something really weird and
yeah.
different from that. Yeah.
Okay, any other thoughts on this topic here? Okay, then, yeah, model representations, which is, yeah, a bucket of different things again. Um, this one, Jose started thinking a lot more about, so hopefully we'll also be talking about that more in the next weeks and figure out more answers there. Basically, like how can we represent symmetry in our models and in the outputs from learning modules? So yeah, basically, one, we have a lot of symmetric objects in the world, and it seems redundant to store all the symmetric information about them, plus to have hypotheses about all the symmetric rotations which we currently have. And then two, when we send output from one learning module to a higher level one, that needs to encode some information about symmetry, because otherwise, just by pure chance, you might recognize a symmetric object in one orientation and send that up, and then next time you see it, the rotation you infer is along the symmetry axis, and you send that up, which to the receiving learning module looks different, but it should actually be the same. And so, yeah, Jose is looking into how we could do that, maybe representing it with symmetry groups, and that would help both cut down the number of hypotheses we test and make inference faster, improve how we store our information about our models, and also solve issues we have with the compositional models, and storing rotation of child objects.
Yeah, and just on that, I think one interesting thing that's kind of came up thinking about it after the TRM is like, so we talked about the problem of like, okay, we're doing inference. Now we have this list of kind of candidate symmetric poses, and we want to match it to our stored symmetry representation. And we were talking about like, okay, how are we going to kind of match that to like, oh, this is C4 group with this canonical pose. But what's interesting is that like that issue also applies to even if we do like the list method. So like let's say we've stored 0, 90, 180, 270, and now we're inferring the object and it's 10, 100, 190, 280. Somehow we need to like it's still a non-trivial thing to match those two. In the like kind of 1D case or like just a rotating square, it's easier because we just have these like, okay, well, it's 90 degrees. Maybe we just store it as like the relative difference. I guess the point is like, even with the list method, which was kind of going to be like our fallback, we probably need to come up with a richer representation like relative
Yeah.
orientation. So like, it was interesting to me because it like basically the list fallback isn't as I think we kind of thought that'll work. It's just going to be unelegant and maybe computationally expensive. But actually thinking about it, I think we do, no matter what, need some sort of richer representation of like relative pose or something. So, um, yeah, basically exploring what Jose's identified seems like a definitely worthwhile thing.
I was actually going to say that the example that I know that you wrote that example in the shortcut, but that's like, yes, we definitely need to consider relative rotations. And I know that, with the 1D example, like we can see that there's only 90-degree differences. So, you can kind of factor out that it's 0, 90. But it's the same for 3D. Like we can't see that
It's
it's
harder to
90.
imagine. Yeah.
Yeah. I mean, we can't see it by number, but the equation that I wrote, like what is the rotation between two matrices, two orientation matrices, is I mean, it's trivial. So, whatever list of orientations that we get, in 3D, we can always get the relative rotations. That part is not the hard part, thankfully. The hard part is after we get that list, can we fit it into this kind of, is this list of four C4, or, is it actually
Yeah, that's what I
duplicates and
mean.
what?
Right.
Yeah.
Yeah. No, I agree. That's the harder part.
Yeah.
Yeah. And then I guess another thing to think about at some point when developing this is like, how would the brain do that? Because with the list method, you can kind of imagine how you can learn associations. Like this is equivalent to this. This should activate the same activation, but the more mathematical it gets, the harder like to think, oh,
Right.
how would the brain actually elegantly solve this issue? And yeah, I guess if we find something that works and it's really elegant, then maybe the brain has figured out an equivalent. But still, if we run into a dead end, that's often a useful way to rephrase the problem and think of like a novel solution again.
Yeah. Yeah, I agree. Because yeah, especially like, okay, let's say we store like the relative orientations and we're matching that. And then okay, again, maybe that's associative. But then like with something like a circle, which sorry, a sphere, which kind of has essentially infinite symmetric rotations, um, how are we representing that? And it, yeah, I don't know. And then, but maybe it's like we just need to think about it in like a different way. Like maybe the brain, it's more like throwing out rotation information as it gets more symmetric. So it's like it doesn't care about the concept of rotation when it comes to a sphere because it's not really predictive. And so it doesn't store it at all or something like that.
Yeah. Yeah, I'd also be curious whether the models actually um, are different for symmetric objects. Like, do you need to store the same features 4 times if it's, or however many times around that axis as they repeat? If you know that it's symmetric around that axis, um, if that makes sense. Like,
Um,
Yeah.
can
as
you,
in like if the faces of a cube are like the same or
yeah,
yeah,
like,
like is there a way to uh kind of reuse the representations?
right.
Yeah, that's interesting.
I think it
And
would
that
be a
would
way
get
to.
more into like actually modifying the movement input in a way that it keeps predicting the same feature if you're going along the axis or if
Yeah.
you're going orthogonal to the axis of symmetry. Sorry, Jose, I think you want to say something.
Oh, in terms of how like it happens in a debate, like if I have something approximately square, it's not exactly square, but like when I think about symmetry, I think about 0, 90, 180, 270. Even if I observe the object at like an angle, I'm not thinking about this as a list. I'm not thinking about the list of the symmetry as like 45, 145, like 135, whatever. I think of it as like, okay, it's tilted, but it's still 0, 90, 180, 270. Like, at least in my brain, I kind of think about it that way. So I feel like the brain probably recognizes like some kind of like, okay, the pose that I'm seeing is not the usual pose, but it can
Or
infer like what that
as in
is,
like
and
the
then
symmetry of it is sort of orthogonal to the current pose.
yeah, like I feel like the brain probably like factors out the relative rotation. Like it's probably not storing a list of all
Yeah.
the like absolute poses, but like one pose and like with the relative rotations that can get you to the other
Yeah.
poses that are symmetric.
Yeah, it's like it's 45 degrees from the default, and I know that
Yeah,
it's whatever C4 symmetric along
yeah.
that
I
axis.
agree that it probably doesn't come up with C4 because that's a concept that I learned like in group. Like I didn't take group theory or abstract algebra. I mean, so but I think that the reason for using I think the reason for using that is not necessarily elegance, but it's just we can just take advantage of some math properties that apply to group theory. So I think one that we talked about in those was like, for example, if you have C4 like 0, 90, 180, if even if you figure out only 0 and 90 and you know that it's C4, then you can actually derive 180 and 270. Like all the symmetric operations are compositional in the mathematical sense, as in if you figure out the 90, then you can apply 90 twice to get 180, and you can get the 90 3 times to get 270. So let's say Monty, like I know Monty gives up the list of all the symmetric like poses, but for whatever reason, let's say just drop the 180 and the 270 part. If we still like say that, oh, this is still part of like C4, then we can kind of recover the full list of symmetric poses. Um, Even so, it gives like a little bit more tolerance like even if Monty doesn't give like the full like I don't know. I mean, I'll see like how Monty classifies a cube. Cube has 24 symmetries. If it gives all 24, Monty's great at detecting symmetry. But let's say it gives like 22, but it's like really, really close, and we can actually recover the like. So I don't think the brain does this, but it's just like we're gonna take advantage of math so that Monty is a little bit better than human brain in this aspect. And I think that's okay, like to do in this case.
Yeah, I think it also fits with like the general theme that we've been keeping Monty kind of interpretable, um, at least for the time being. Like our representation of pose is going to be even more interpretable, more symbolic with this than it would be otherwise than just like a messy list of poses. And like
Yeah,
I don't know, if one day we want to develop a SDR type thing that is just based on associative connections, then maybe we do that. But but yeah,
yeah,
until we're kind of going down that path, I don't think there's any harm in it being kind of again kind
right.
of quite explicit.
Yeah. Also, if I think about a cube, I know there's 24 because I learned it, but actually, like if I try to identify it, then I had to like, actually like really think about it to get all 24. And I might not even get all 24 because there's just so many rotations like in a cube.
Yeah, again,
So
it feels like when there's a lot of symmetry, it's more like our brain is kind of just throwing out or like just not caring about information rather than saying, uh,
right.
"Oh, this
Yeah.
is definitely equivalent to this." It's like it cares about the rotations that are not equivalent. Like I don't know, I guess yeah,
Yeah.
turning this by a tiny amount is not equivalent to turning it by 90 degrees. Um, and similarly with a cube, like if we just put it on its edge, like then that's not kind of one of the symmetric poses. But
Yeah.
um, yeah,
Like all is to say that like my I don't think my brain actually stores the 24 rotations of cube in like the in my object model of the cube in my brain. But it like somehow kind of infers them out. But in Monty, I mean, we're gonna learn them, we're gonna sort it with a cube, and we're gonna use that during inference. But anyways, well, we'll see how it goes.
Yeah.
Yeah.
So yeah, hopefully this will turn from red to at least blue or green this year or in the next month. And then I guess maybe related conceptually is representing repeating patterns efficiently. I think I also added uh, one here, modeling repeating patterns. Yeah, so basically think of patterns on bed sheets or on a carpet where you have an object or a structured pattern that repeats many times. And at the moment, we would need to learn or infer the pattern over and over again for each location where it applies. The simplest one is to think of like a checkerboard pattern, which is very regular. We are very good at making predictions, but it doesn't really seem like we learn like a large scale model of like a huge checker pattern. You're just able to like extrapolate from the general pattern to how it should continue. Um, and so, yeah, question is how could that be represented efficiently? One idea could be that the model's reference frame kind of wraps around itself. So when incoming movement information would take the learning module outside of the reference frame, it instead integrates the movement so it predicts coming out on the other side of the pattern, kind of like how in some video games you can move off the left side of the screen and you come back on the right side and reappear. And that would be like kind of like a toroidal space, but like yeah, what grid cells can do. Um, oh, I think there was just an earthquake. Uh, um, but yeah, that's just one idea, and there could be other ways to represent repeating patterns more efficiently. Um, so yeah, just on that list.
yeah. The I guess it also relates to kind of like um feature models or like kind of texture models, whatever we want to call them, being kind of learned and bound to like 3D models and um, yeah, the kind of
Yeah,
efficiency around that. there's a there's a very apt animation. I don't know if anyone's seen this old like Christmas cartoon from Disney, but where what do you call it? Oh, I shared it in the chat. Yeah, GIFs are, I guess,
Oh,
kind of hard to, um, but basically where there's like this checkered paint that is like applied nolly. Anyways, I can't share it as easily as I thought. I'll yeah, I'll send it after the discussion.
okay. Um, okay, and then yeah, again, we a bit related representing sets. So like some objects seem to be just defined by a set of features that have no particular arrangement. Like, I don't know, your outfit for tomorrow consisting of a t-shirt, pants, and socks and whatever, but they don't need to be in any arrangement. You can just throw them on a chair and that's that. Or we talked about the drum kit just being like a drum and two drumsticks, but they don't necessarily need to be in a specific arrangement. Um, and yeah, one idea we were throwing around were 0D models where the learning module just doesn't get movement input, it just stores a union of features that could all exist. But yeah, that wasn't really a completely accepted idea, and so still looking for other ways we could represent sets of features that don't have specific spatial relationships. And that becomes more important as we go more like deeper in the hierarchy of Monty and we have more abstract models. Yeah.
But also kind of like behaviors, because like a drum's particularly interesting because you can like, I don't know, play drum with it, and the sticks have kind of relevance to the yeah.
I was gonna ask, like, are we thinking about things like the dinner set, where the dinner set has like, fork, spoon, whatever, but technically they can be arranged in like different ways. The fork is on left, fork is on right, and so there's that.
Yeah, I guess that is an example because yeah, you could have a reference frame for the dinner set, which specifies how the table should be set, but then you also have a representation of like the items you need to set the table, and they don't have any order. So I mean,
Yeah, so I'd say like historically when we've talked about the dinner set, we haven't meant this. We've meant more like an arrangement of objects that
Right,
do
right.
have like a specific arrangement that we
yeah.
recognize. But yeah, like you say, it could be more flexible.
Yeah, then we have here two related items, which is representing where an object ends and dealing with incomplete models. I think I also have one here. So yeah, basically Monty right now, it can't distinguish between having learned an incomplete model of an object, like for example, it's only seeing the car from one side, so it wasn't able to see the other side of it and store any features for that, versus actually moving off of the object onto a different object. Because in both cases, our hypothesis takes us away from any points stored in the model, but there's no concept of, oh, this object actually, we know that this object ends here, versus we've never explored this area before, so it might still be part of the cube, and we should just incorporate the new information into the cube model. And so, yeah, again, still a bit unclear on how we would solve that, but representing where an object ends or using information in the surface normal for that could be one way to deal with it. Yeah.
I read the surface normal as like surface model, and I was like, oh, that sounds like a good solution actually, because like if we have it in points, and if the point is missing, then we don't know if it's an incomplete model or it truly nothing is there. And if we have the model as point clouds, but if we have a surface model of the object, I feel like it'll be kind of weird if like the surface doesn't close or something, like, or just kind of abruptly kind of. I feel like that maybe like inside representing a point cloud, maybe like some kind of volumetric or surface thing could tell us like, oh, we're not actually done exploring. It's just, yeah. I don't know. I feel like I thought it was. I read a surface model. I was like, oh, that could be a good way to kind of represent.
Yeah, when
Or,
you say surface model, do you mean the 2D surface model? Like,
no,
or do
no,
you
no.
mean
Sorry,
a
like
different
the
type of
the
representation?
surface of 3D. Like
Yeah,
the triangular meshes. Like think about that. Like if a random triangle is like missing, it's probably not that there's a hole. I mean, there could be a hole in that object, like in a vase or something. But most likely, it's just that we just didn't see that particular like that region, and we should probably like fill it in or something.
yeah, yeah. And in a
Um,
sense, having the surface normals give us an approximation of the surface
yeah,
of
that's
an
true.
object.
That's true. Yeah,
Um,
yeah.
and so we use that a bit in our current modeling, our current matching algorithm. But there's also um, yeah, another item for better surface
Yeah, which
representation.
I don't think we linked to this one right now because it's a fair point that they're related, so maybe that's worth adding.
I think we do, but it looked like the link didn't render.
Yeah,
Ah,
like the
okay.
markdown surface representation levers. Okay. Probably because actually I don't know why. Okay, well.
On that. But yeah, basically right now we are kind of taking into account the surface normal direction and the amount of curvature to do our matching. And so we have an estimate of the surface
Right.
that we
Yeah.
use, but not one that's used for this problem of like where an object actually ends and whether we should extend the model or not when we do unsupervised learning.
Yeah.
Tristan.
Interesting. Yeah.
The just image popped into my head when you were reading this, which is a pile of wires where you pick one side and you don't know which other end it actually is connected to. So the reason popped in because it's a one-dimensional problem. And where this object end is unknown. And then like I'm just wondering if that scenario, that test hints at like figuring out where object ends. There's no, because I've seen a lot of surface normals and I'm like that assumes a lot, but it's like here's a one-dimensional problem that also we don't know where the object ends and how do we know that it ended like in a single wire if I'm pulling it out of a pile of like how do I know I'm not done yet? Like what tells me of like I'm conscious of like there's more to pull, there's more to pull, oh I'm done. And it's one
Yeah.
dimensional, there's
Like a
no 2D math.
discontinuity. Like once you
Right.
detect a discontinuity, then you've detected
Right.
the end.
So I just want to throw that in there that maybe that narrows the scope significantly.
Yeah. Yeah, so like you don't have a model of the cable yet, you don't know how long it is, but you can tell that like you're not at the end yet until you get to the point where you have the full wraparound. Yeah.
That's different from that throws a wrench in what I had just been thinking about. It's a different approach. I was just thinking about knowing what you don't know by sort of fitting this thing you're observing to combining that with like a sort of proto object. Like you roughly know the boundaries of this thing that you're observing. So if you roughly know the boundaries of this thing that you're observing and you don't know that you have seen the back of it, you still have some representation of the approximate spatial bounds of this thing. So, if you have both of those things together, both your detailed object model plus a bounded region in space, you could know, hey, here's this bounded region that I have not explored. So there's still some representation of the uh, bounded surface, bounded area. So it's not just like, nothing in a model. There's still model. It's just unpopulated. If that makes sense.
Yeah, or
Yeah,
like a
how
potential
would you?
mismatch. Like maybe there's nothing in the model, but there is something in this model free space. And that's
Yes,
kind of what tells us that there might be more to see. Um,
basically, yeah. Um,
Yeah, I think both that and the cable problem are like those are both like finding the end of an object within one encounter of the object versus like the dealing with incomplete models is kind of like you learned a partial model of an object because you've only seen it from one perspective, and then you encounter the object again. Um, well, I guess it's still similar in the way that then you can still use those model-free heuristics to tell that the object is actually larger than what your model has stored. So yeah, never mind.
yeah, the wire one is interesting because it feels like, you're not necessarily building like in my case, when I was thinking about something sort of mug-sized or spam can sized, I do know what the approximate spatial boundaries are, or I can make a pretty good guess. Like I'm not going to guess that this mug just continues on, like its depth wise is going 5 miles that way. It's not like a railroad track. You know what I mean? But I still have some sense of that. But with a wire, it could be very long. I don't really have a sense for, what an approximate length of that thing is until I pull it out.
yeah. Yeah, and I feel like with this one, it's also maybe helpful to kind of think about like there's sort of like elements about like policy and like how we act when we explore an object like this and how we represent an object boundary. Like whether it's a 3D mug or a wire or whatever, like we could have kind of some intuition of like, okay, yeah, there's sort of more, so I'm going to keep following it until I reach an end. Um, and then, but then there's also the question of like, okay, how do you actually represent the sort of discontinuity when it does stop? Like, is it just like, is there something sort of special about that point? Um, and in like in 1D space, maybe we could say like, yeah, it's an endpoint, but then that's the weirdness of like surfaces, like,
I mean, I
um,
think it's actually not that weird because with the cable, you also know it where it stops in the other dimensions. Like you know in which direction you should keep moving. You know if you move in the direction of the surface normals that you're currently sensing, you'll not be on the cable anymore. You know
yeah,
that it won't continue there. So once you get to the end of the cable, the surface normals are wrapping around. So you know the object won't continue in the direction of the surface normals there either. And so, yeah, you might
yeah,
just be
yeah. So
using
like surface normals maybe are sufficient. I guess it's
yeah.
yeah. My point was just that like yeah, there's maybe uh, two ways or like different ways you could approach it. Thinking about it, like one is like how you're moving and like basically deciding to continue exploring because and then the other is like how when you store the model, how is it kind of represented that it's like an end and maybe those are related. Maybe the movement is informed by the same thing that you would store, but maybe they're different. Um,
Yeah. Yeah, I think in my mind, the big part of this question is like, how do you actually represent it in the model that you store then? That next time you encounter it and you try to do matching and you move into the unexplored area, that's not necessarily evidence against that object. It's just, well, we just haven't seen this, but we can tell that the object can continue in this direction. Um, just to know that you are still on the same object within one encounter of it seems like, yeah, we can just use information, model-free information about surface normals and following the direction orthogonal to them to know that we're still on the object.
but yeah, it is interesting. I don't know in the cable string example, if you kind of start on one end and you randomly jump to some other part, like you don't necessarily know, I guess, that you're on the same, um, in that case, then yeah, it could be another cable or
Yeah.
so.
Okay, so there's that. We have learning abstract models, which, yeah, depending on how we define abstract models, might just emerge naturally at higher levels in the hierarchy. Basically, there's models that get input from other learning modules, so they represent more abstract information. They might require learning new movement vectors in conceptual space, or somehow mapping them onto physical movement. It's just something we haven't really played around with yet, and so don't really know what we're going to run into here.
Yeah, I can imagine this one branching out into multiple unsolved problems when we start tackling it.
Yeah, right, yeah. And we have some nice to have ones, which is performing efficient, efficient nearest neighbor querying. Like I'm pretty sure the brain doesn't do KD search, but it seems to be the most efficient implementation we found so far. So, like, is there something better? Still, it's the main bottleneck of Monty's computations right now. But yeah, this is more just of a speed improvement. It wouldn't add a new capability to Monty. Um, and then another, American is nice to have right now because I don't see any benefits of doing it, but it's a conceptual change we talked about many times before of communicating displacements instead of locations. And yeah, like we talked about in London, that we could do that. If we don't vote on locations, we could do that today. But it just doesn't seem like there's any clear benefit in doing that, besides it maybe being more how the brain does it. Any more thoughts or questions on this topic of model representations?
Nothing specific except for feels like there's some connection between the canonical views and the abstract models.
Oh, interesting. In the sense that the canonical views are more removed from physical reality.
Maybe, yeah, I mean, in the
And
sense
they are,
that they also kind of represent something, there's a genericness to a canonical view.
yeah. And that they maybe require learn mapping movement differently, or
Yeah, maybe. Uh,
yeah.
they both kind of represent some kind of, yeah, I guess generic is the only way it's the best word that's coming to mind for it.
Yeah, maybe relating to object categories too. Like,
Yeah, yeah.
Yeah, and or I don't know if also if you're thinking is in like almost kind of like the displacement LM or like an edge-based one, like you could imagine maybe it's easier to recognize certain children objects, like I don't know, an eye and a nose, and sort of matching the connection between
Mm.
those is sort of how you recognize kind of the face in 3D. I don't know. Where yeah, basically we don't care that like I don't know the eyes are slightly behind the nose and all this kind of stuff. It's more just that there is like a relative arrangement of them. Mm.
yeah. So yeah, I'm sure we'll get back to that at
Like
some point.
yeah, just like to say like a Picasso or something like super abstract like that. Like there's probably no depth cues in that to or very little depth cues to tell you, oh, this can match onto like a 3D model. But we recognize the eyes and we recognize lips, and we know that when those are in kind of these sort of abstract configurations, that is a face. Kind of.
Yeah.
I could, yeah, maybe it's worth adding under the recognized 2D just like more abstract because I'm not, I mean, maybe that's kind of like a canonical view, but it feels like that's getting more towards like displacement elements and sort of like throwing out a spatial metric of any kind.
Like without depth cues.
Yeah.
Yeah, I like that it might be a different problem. This might just be generalization and categories, but yeah, good to keep it in the mix. Okay, and then the last two, I think, yeah, goals and actions we might go quickly because there's lots of open stuff there. But one thing that I feel like is, at least in my mind, the biggest like big open question, a big thing to figure out is unsupervised learning, especially now within a hierarchy. Because yeah, up to now, I mean, Monty can do unsupervised learning to some degree, but it learns objects in a void. There's only one learning module or a few. There's no hierarchy, and now that we're using hierarchy and we're using more complex scenes where there are multiple objects and child objects in the scene, we currently have to hold Monty's hand quite a lot and help it kind of learn the child objects in isolation first before we show the combinations of them and stuff like that. And we talked about how that might be an okay assumption, like children learn objects in isolation often as well, and we don't learn that well about something new if it's in a very cluttered environment. We try to isolate it somehow, but still there need to be some improvements made. And so yeah, there are a lot of different related items on that topic. So one I just mentioned, knowing it. Oh no, that's not what I mentioned, but yeah, basically weekly supervised end-to-end training. So for example, just showing a compositional object and telling it what that is, but then it identifies subcomponents of it by itself and knows at which level in the hierarchy to learn about child objects versus parent objects. Yeah, something that ties into the whole unsupervised learning topic is temporary models, learning speed, and consolidating memories and forgetting them. So yeah, learning temporary models is important for interacting with the environment, but also for memory consolidation. And currently Monty can learn models very quickly. So basically all of Monty is kind of like the hippocampus where it can instantaneously store information, but it doesn't forget. And so one idea is to introduce a learning speed parameter where learning modules can learn at different speeds. For example, at the lower levels in the hierarchy, you incorporate knowledge at a slower rate, but you also forget at a slower rate. And so you have more stable models in the lower levels that the higher levels can then depend on more, and they can form more temporary models of those objects in composition. And yeah, we could use constrained object models for parts of this, also for the consolidating memories and forgetting. They already have kind of a mechanism for forgetting things that don't reappear. But we haven't really tested them too much yet. And we probably have to add this kind of learning speed parameter, figure out how that would work, figure out how like merging models or forgetting about entire models instead of just points within a model could work. Because yeah, constrained object models, they just find statistically significant points within an object, but then if an object is only encountered once and never again, it would still never be forgotten by Monty. Which maybe it's fine, but probably it's not, because probably we would want to merge it with something else to learn a more general representation or not care about it in the future. And then, yeah, related to learning speed parameters, some way to ensure stability of lower level models while being able to adapt to changes. So that the thing I mentioned about learning at slower speeds in the lower levels. So the next higher level gets more stable inputs that it can use to learn its models and doesn't keep getting changing inputs because the lower level keeps learning new things. And lastly, related, classifying whether an object is new, so never seen before, or whether it's something we've seen before and we should extend that model. And we can do that to some degree. That's what we do in our unsupervised learning experiments. Basically, if none of the objects we have in memory have positive evidence, we're saying we don't know this object and we learn a new model of it. But that's a very extreme threshold to have negative evidence for all of the objects we know about. And so if we encounter a new object that's a bit similar to an existing object, we would not learn a new model for that. And
Yeah,
so, yeah,
that feels like I don't know if this came up already in the conversation about burst sampling and unsupervised learning, but that seems like another thing where we have to rethink it because that condition I think is almost impossible with burst sampling. Because we'll
right.
probably keep generating new hypotheses, and they'll at least get one step normally of like, okay, yeah, this evidence is okay. Um, and so just basically coming up with like a new like, okay, you've been bursting for a long time. It's time to try just a totally new model. Um,
Yeah, right. Um, and yeah, one other thing we talked around there was that, yeah, we could always be learning temporary models and then use memory consolidation to see whether it should be incorporated into existing models or new models, which is kind of a bit what Monty does. It always learns kind of a temporary model in the buffer within an episode, and then at the end we decide whether to incorporate that into an existing model or create a new model from it. Um, but so yeah, those are all quite entangled with each other, and in my mind still like a big area of uncertainty. But yeah, pretty important for real world applications of Monty where we can't hold Monty's hand too much. Uh, all the learning modules at different levels in the hierarchy need to be able to figure out what they need to be learning in a more complex environment. Yeah. Any thoughts or things that are missing here?
maybe like on unsupervised learning, what you were just saying made me think, I don't know if we want to add something about like remove concept of episode or like separation of inference and learning. Um, so like Monty's already pretty good about that, but like as you were just saying, like right now we have this concept of like the buffer storing like a set of observations and then deciding to do something. But I think it would be better for the long term if like basically every time Monty interacts with the world, there's a little thing that changes, and if that happens enough, then that is learning. Like that would feel more brain-like, and then that would also just uh, it'd simplify how Monty like how unsupervised learning happens. Um,
Yeah. Yeah, I added it under consolidate memories maybe for now, saying, yeah, in a post-episode world, when do models get consolidated?
yeah,
Uh, maybe,
yeah. Is it constant? Because like right now in our unsupervised learning benchmark, I'm assuming we reset Monty between um, presentations of
yeah,
objects. Um, but so like assuming we relax that constraint a bit more like the unsupervised inference,
yeah,
um, how does it how does unsupervised learning then work?
yeah,
Um, and I mean, what's cool is I think the grid object models could already do this pretty well. Like I think because they have this like notion of like a number of observations in a cell in a voxel. And I think that's constantly just being incremented up or down with some decay factor, and then there's like the threshold that says like, okay, is this a permanent feature or not? Is this part of the model? I think that would or like that's basically the key mechanism we probably need. The challenge is maybe finding like the hyperparameters that result in stable learning, but maybe that kind of relates, I guess, to the learning speed parameter stuff.
Yeah. Yeah, and I guess the signal for like updating them could be when our hypothesis changes from one object to another object, or uh
Yeah, well, I guess I'm wondering if like the update would just happen constantly. So like, I mean, like
yeah.
we would only be updating a model if we were in that hypothesis space. So I guess we'd need like a threshold for that or something that we wouldn't the sort of the reference frame needs to be, yeah, like sufficiently active to we don't want to update all reference frames constantly.
Yeah.
I guess yeah.
Um but yeah, so if people want to think about this space, I think that's one of the more urgent ones, also for kind of the follow-up work on compositionality after this quarter, figure out how we can learn compositional models with less supervision. Um, those will all be important questions to ask and answer there. And then, yeah, the last big one is goals and actions. So manipulating the world to achieve goals. I just put this big one up here, which is kind of this large new capability that we want Monty to have. And since this is still red, it's still unclear what all we need to achieve this. And so the whole space of questions might grow here as well. But some of the ones that we already identified is like, how do we learn causality? So we propose to use kind of an STTB-like mechanism to learn associative connections between learning modules or columns and their object and state representation. But yeah, I think there's still quite a bit of uncertainty around how it would work exactly. The system needs to be able to define its own goals, or learning modules themselves at least, and decompose goals into sub-goals. So if there's no external goal provided, a high-level goal could just be curiosity, try to gain more information about the environment, learn better models of it. But how do we turn this kind of vague objective into concrete goal states and target poses? Still pretty unclear, at least in my mind. And then, yeah, that relates to decomposing goals into sub-goals. Talked about using the learning module hierarchical connections to decompose goals somehow, but I guess emphasis is on somehow. So, yeah, and then maybe related to this is model-based planning. So if you have a goal and you have a model, you can use that model to plan actions, maybe find sub-goals or a sequence of motor commands to send out subcortically.
Yeah,
And
does
yeah,
this kind of relate, oh, sorry, to,
yeah,
to
go
like the
ahead.
distinction in Milan that we started kind of making in sort of language of like the
Yeah,
goals and
yeah.
the sub
So
goals is kind of like discrete states. This is more like movement in a space.
right,
Um,
yeah. So yeah, sub goals, yeah, like you just said, it's more about if you have a goal state, so like a state in layer 3, you have a way to get to that state, which leverages other models. But then if you have a target pose, you can leverage the reference frame to do path planning. Um,
right. And yeah, and I
and
think like
yeah,
one concrete example we discussed was like you can imagine some problems which you might formulate in either way, where like if you had like a joystick kind of thing that could be in four kind of positions like north, south, east, west, you might think of those as kind of like goal states, like, oh, it's in this north state. Or you might break it down as like, oh, I want to be in this target pose, and like, what's the continuous action that I need to execute? And maybe our brain is doing a mixture of both, and kind of they sort of execute different, they sort of recruit different systems, or yeah.
Yeah. Yeah, and I think at least the last thing we said on was that with goal states, you can't really path integrate. You have to
Right,
traverse all the edges of the graph, so you need to have moved the joystick between the different positions. But then with
right,
path planning in a reference frame, you can do that. So if you've never moved it from north to south, only south to north, then you can figure out how to do the reverse. Um,
right.
and yeah, there's loads of literature on spatial navigation in the hippocampus. So probably doing a literature review there could give us some insights in how we could do path planning with object models. And yeah, I think one question we had around there was also like, should this happen inside columns? Should we plan in a shared egocentric reference frame? Should we leverage model-free mechanisms to reach a target pose? Yeah, so still, yeah, some ideas here, but still some open questions. And then related to planning is also simulating consequences of actions and choosing which ones to take. So we have models of objects, behaviors, and causality, and somehow we need to use those models to simulate possible actions and their consequences. Naturally, there are kind of infinitely many actions we could simulate. So how do we pick which actions to simulate? What are the most promising ones? And then maybe this is more of a biological question, but how to distinguish simulation from reality, something we talked about various times. And then, yeah, lastly, coordinating actions of multiple actuators. Talked about maybe having models of actuators, like in the model of a hand and motor cortex, and how those can behave and depend on each other. That for smooth coordination between multiple actuators, we should rely on subcortical mechanisms and practice, but still we can use deliberate or slow model-based coordination to like do new combinations. Like if someone shows you a new hand sign, you're able to imitate that without like obviously if you practice it more, it becomes more natural, but you should be able to leverage models to coordinate multiple actuators. Yeah, so that's all I had on this topic here. Any thoughts or things missing? I'm pretty sure there are things missing, but things that are clear that they're missing.
I guess what, so I'm also just looking at that sort of like mind map we made of like open problems. And I was just thinking, so one, we have like object recognition of volumetric deformations like the clay and stuff like that, and the t-shirt. But I don't know if it's worth mentioning for now. Maybe we could put it under the model-based planning. But like, how do we manipulate, I don't know, objects that have, uh, yeah, things like clay or a t-shirt, and like how do we plan manipulations on those? Like, because in that
Yeah,
case, it feels more similar to this model-based planning, maybe, in that it's like there's not like a discrete state of like, um, we're kind of able to manipulate arbitrarily.
yeah, yeah,
Um, and then I don't know if this is, yeah, in some ways it's niche, but maybe but like things like shadows and and stuff like that. We talked about recently, like how we kind of um
Maybe in model representations or
um was as in like that objects cast shadows and um I don't know, like at the least we seem to kind of incorporate information about that into how we infer the world. Like it seems to be part of our models. Like I mean, the classic one is the, you see that checkered square and you think it's the same color. Um,
yeah. So yeah, I was wondering where that would fit.
yeah, I don't
I
know.
would say model representations probably.
Oh,
Or
right. Sorry, you meant as a super category. Yeah, sorry. I
yeah.
just saw you pointing at deal with incomplete models.
Oh,
I
sorry,
see what you
no.
mean. Yeah, yeah. Right. Yeah, so like it's almost like shadows, optics. I don't know. It feels related to also just like things like occlusion. Like at some level we have an understanding of like, oh, I can see this object, like I can see this surface because of where my eye is relative to the object. Um, like that again, that feels like somehow we've learned that that is a limitation of our visual sensor. Um, there's not really a concept like that for tactile sensors. Um, so I don't know, like maybe one summary would be like uh, optical
How
scene
about
level properties or something.
incorporating shadows and occlusions into our predictions?
Yeah, yeah, I think
That
yeah, maybe
possible?
just for now at least, and then I don't know if it'll become more concrete, but
Yeah. Yes.
like reflections, I guess is another weird one. Like, uh, is that Link?
Yeah, I just got a cup of tea and he said birthday.
Oh, nice. That's cute. Um,
I have another one, potentially, another topic here, which
Yeah,
is Monty doesn't really model itself. It doesn't really explicitly model Monty.
yeah.
I don't know if
Right.
that'd
Maybe
be
that
one.
falls under manipulating the world. So um, modeling on uh, actuators or
Mhm. Modeling its, and I also wonder if this also kind of fits into
oh yeah, I have it
oh,
here. Learn models of body and
okay,
action space.
cool.
I marked it as blue because I feel like um, we would basically use the same algorithm we have for learning any models, but
Hmm.
using proprioceptive input instead, or the more reference copies of what we did.
Right.
Um, but yeah, so just one caveat, I guess, is that everything that's marked in blue here still might turn red, or like it's all stuff that we have some ideas, but they're untested. So not saying that everything that's not red is like all resolved and clear. Um,
Another one, maybe, um, might be like kind of rapidly growing or shrinking models or kind of adapting. Maybe it's clear with like an example, but like, we've talked about like seeing the stapler arm move for the first time, that we sort of like maybe we use attention or something to separate that out as like a distinct child object. Or like another one is like if you have an apple, you've never seen it cut in two, and then suddenly it's cut in two. Like what is kind of happening at the like somehow it
um,
feels like we're at least adapting the model we already have very quickly. Um,
oh, so
and
it's beyond segmenting it. You mean more on the prediction side of things?
yeah, it's more on like the model representation side. Um,
Yeah. Maybe I'll add it in the text under here.
sure. Yeah,
Um,
just to think about it. Um,
Yeah.
yeah,
Any other ones? But yeah, otherwise, I think we talked about a lot of things now. Yeah, to
It's
me,
nice
it's
to get
actually,
a overview because you
yeah,
kind of
it's
start
actually
seeing where things might be connected.
right. Yeah, it helps to put it all on a map, and it's kind of nice to see like this as a finite list of things.
yeah. It
Um,
honestly feels encouraging. Like, not that
yeah,
things are easy, but
yeah. I mean, yeah,
yeah,
like I said, we still have all the blue items here that also still need to be tested, but it feels like this is a manageable set of fully open questions. Nothing that seems unsolvable. And so, yeah, hopefully looking at them in context of each other and uh, coming back to them, we'll be able to figure them all out.
yeah. And I feel like, yeah, some of them you could almost have like you can imagine them being like darker red. Like it's like, oh, that's kind of hard to think about. But I feel like most of them are kind of a light pink. Like with all the things we've written here, like we have a reasonable set of things to try. Um,
Yeah. Yeah, some of them are already kind of turning into blue, like I
right.
guess the symmetry and attention, we're already starting to test ideas and uh, yeah, so probably have to update that at some point.